Welcome to this lecture. This is the fifth lecture of week 1. In the previous lectures, we have introduced the concept of LP spaces on some appropriate measure space, or more specifically in the case of probability spaces. The conditions that we require are on collection of measurable functions, we introduce certain kind of integrability assumptions. What we have also seen is that on these LP spaces there is a natural norm that comes in. So, we have verified those properties, and then coming from the norm we have induced a metric topology on it, and we have also shown that in that metric topology the LP spaces are complete when we are choosing P between 1 and infinity, 1 included, infinity excluded. So, therefore, LP spaces become Banach spaces. So, in this lecture we are going to continue similar discussions, but we will focus our attention to several related spaces. So, without further delay, let us move on to the slides. So, as just pointed out, we have already shown that these LP spaces, which are real valued measurable functions with certain integrability assumptions, this collection forms a Banach space, which essentially means it is a complete norm linear space. So, let us move on and look at the first related space that we are going to discuss. So, from the previous one we will make a small change. Consider the extended real line. This is essentially the set of real numbers together with plus and minus infinity, and as soon as you include plus and minus infinity, there is a usual extension of the algebra that we know. So, you have to again define a real number plus infinity as infinity and so on. So, therefore, that is the standard arithmetic that you extend, and therefore, you get the relevant algebra. So, then consider extended real valued measurable functions now with the same kind of integrability conditions. So, now we are continuing with this measure space. On top of the measure space we are looking for collection of functions which are now extended real valued. Now, with the extended real valued setup, we also have the appropriate Borel sigma field and all that. So, you can talk about measurability of functions, and then for such functions we also want this integrability assumptions that essentially describes this collection. This collection of functions which we now denote by LP mu r bar. So, we carry this values space on in the notation to clarify the distinction with the previous LP spaces. Now, here as considered in our discussions earlier, we will continue with this choice of P, and we will see the need for this soon. Now, if you take any extended real valued such an integrable function, then what happens is that as a consequence of the integrability assumption, which is again that the integration of mod f to the power p should be finite. So, under that integrability assumption, what we are going to get is that the set of points where your function takes values plus and minus infinity, that should have measure 0. Now, you see that if this set of values or set of points were to have positive measure, then this integral could not have been finite. So, this automatically follows from the integrability assumption that this set has to have 0 measure. Consequently, the function which we are starting by assuming that it is extended real valued, but now we are saying that by the integrability assumption the set of points where it takes plus and minus infinity as its value, that should have measure 0. Therefore, our final conclusion is that any such function must be essentially real valued almost everywhere. So, with almost the full set of domain points, what you end up having is that the function must be taking real numbers as its values. Now, we continue using our earlier identifications with mu almost everywhere equivalence. So, this we have discussed earlier in remark 1 in the setup of the LP spaces that we have discussed. Now, we may continue to use the similar almost everywhere equivalence, and therefore, identify each such function in this new LP space coming from the old LP spaces. So, let me repeat, we are going to take a function in this extended real valued setup, but then by our recent understanding that all such functions actually becomes real valued, and therefore, this function can be identified inside the usual LP because you have the integrability condition. Now, consider this again this norm function, introduce the similar notation, we look at the pth root of that integral that we assume to be finite. Therefore, if we now repeat the earlier arguments as we have done for the usual LP spaces, we will be able to conclude that this LP space, which is consisting of this extended real valued functions, must first of all be closed under scalar multiplication, then closed under vector addition, meaning addition of functions. Therefore, as a general consequence of those results, you will get that this new LP space becomes a linear space, but together with this norm function you again verify the similar properties and show that this gives you a norm on this linear space. So, therefore, this space becomes a norm linear space, and finally, you follow the similar argument as we discussed in the previous lecture, that as soon as you have a norm, you discuss the metric topology on top of that and check the convergences of Cauchy sequences, and hence if you follow that similar line of arguments, you will end up with the fact that these LP spaces again form Banach spaces. Again, this is crucial that we continue to choose the number p, the parameter p, from 1 to infinity, 1 included, infinity excluded. But now let us move on to a similar setup with another space, but now we are going to look at a more general class which is now complex valued. So, our usual LP spaces were real valued functions, but now we are going to consider classes of functions which are now complex valued. But again, on the complex numbers you can discuss about the Borel sigma field, and consequently you can talk about measurable functions, complex valued measurable functions. Now, you look at mod of f, which is the absolute value for complex numbers, consider mod of f raised to the power p and ask for the integrability condition once more. So, that gives you a new class of functions which is complex valued measurable functions with a appropriate integrability condition. But then again we follow the same analysis as we have discussed so far, and again we can show that this new space of complex valued measurable functions with an appropriate integrability conditions forms a Banach space, and as you expect, the corresponding norm is given by the pth root of this integral that we assume to be finite. So, let me clarify once more. So, we would like to verify first that this space is closed under scalar multiplication, then we will verify vector addition, which is addition of functions. So, from that the natural consequence as it will follow that it will form a linear space. On that linear space you verify that this norm function is satisfies the properties of norm. So, this space becomes a norm linear space, and coming from the norm you talk about the metric topology, verify the convergence of Cauchy sequences and end up showing that these spaces are also Banach spaces. But these complex valued functions have some very nice interesting properties which we will now focus on. So, take any such complex valued function, then point wise you can look at the real part of that value and the imaginary part of that value. So, let me clarify, if I have a point in the domain, call it small omega, then f of omega is a complex number, and therefore point wise you can talk about the real part of f of omega and imaginary part of f of omega. So, therefore, you have this decomposition, and therefore, you end up having for each point small omega a real number which is the real part of the function and a purely imaginary number which is the imaginary part of the function. Therefore, you end up having associating to omega two real numbers, one is real part of f, another is imaginary part of f, and therefore, you have these two real valued functions. This decomposition that we obtained gives you the decomposition of this complex valued function into a real part and the imaginary part. Now, as a general consequence of this construction, what you will have is that this real part of f and imaginary part of f both are now measurable functions defined on this measure space that we have started off with, and these are now real valued. Moreover, you also have by construction modulus of real part of f is less or equal to absolute value of f, and imaginary part of f is less equals to absolute value of f. This follows from the identification that the absolute value of f of omega, the square of that is exactly equal to real part of f of omega square of that plus the imaginary part of f of omega the square of that. If you square it, you will get the absolute value of f of omega squared, and a natural consequence of that is this inequality that we obtain. But then once you have these inequalities, a straightforward calculation involving integrability will show you that real part of f raised to the power p is less or equals to mod of to the power p, and therefore this integral must be finite. By a similar reasoning, you will have imaginary part of f modulus of that raised to the power p, that is now a real valued function. Corresponding to that, we are verifying this integrability condition, and this integrability condition is satisfied. Therefore, this real part of f and imaginary part of f are real valued measurable functions defined on this measure space that we are working with, and hence what you end up having is that each of these real part of f and imaginary part of f are actually coming from usual LP space, real valued p integrable functions that we considered earlier. We may therefore write this earlier decomposition in this space decomposition format. So, earlier decomposition that we have seen was for the function, we split it into two real valued functions, but then we have it in more general setting. Since small f is arbitrary, we end up having this identification that LP mu c is actually I should write it as LP of mu here, essentially with real values which we do not write, and here also we write LP of mu with real number which we usually do not write. So, therefore, correction will be made in the lecture notes that will be supplied to you at the end. So, what we are saying is that all the complex valued measurable functions that we are considering with the appropriate integrability conditions is getting split into these two parts. So, in the our usual LP space that we have discussed. So, this essentially tells you that if you understand the usual LP spaces, then you can talk about the complex valued measurable functions with the integrability conditions that we considered, and also for the extended real valued cases that we also have seen, we have essentially identified with the usual LP space, because by the integrability assumption the functions were taking plus and minus infinity values with measure 0. So, let us just go back and highlight that point once more. So, that we have seen for the extended real valued function case, the set of points where the function was taking plus and minus infinity was actually a set of measure 0. So, therefore, if we understand the real valued measurable functions with appropriate integrability condition, these LP spaces well enough, then we are essentially understanding these two new spaces that we have just discussed. So, let us move on. Now, we introduce a related concept called essential supremum of a function. This concept will be useful because we want to extend the set of p that we can consider. So, remember that we have been working with p between 1 and infinity, 1 included, infinity excluded, but right now we are going to introduce a new concept which is this essential supremum, which will let us define a concept or define a space corresponding to the value p equals to infinity. So, let us see this new concept. So, given any measurable functions, real valued measurable function on this measure space that we are considering, define the essential supremum to be infimum over a certain set of values. What we want is that we are looking for extended real number small c such that this inequality is satisfied, that f is dominated by this constant almost everywhere. So, therefore, what we are asking is that outside a set of measure 0, you should essentially have f dominated by a constant. So, now collect all such constants c and ask for the infimum of this quantity. Remember that since we are allowing the extended real line, in particular c equals to plus infinity, this inequality is always satisfied because we are considering f to be real valued. So, therefore, this set of points that we are considering here is non-empty because plus infinity is always an element here. but then it might also include some other real number C and for which this inequality is satisfied, and therefore, what we will look at the end is the infimum of such a set, and that infimum is what we are going to call as the essential supremum of F, written as S sup by notation. So, this essential supremum now leads us to this new concept. So, we look at this new space of real valued measurable functions once more, but with a new condition that the essential supremum of mod of F should be finite, and that essential supremum of mod of F we associate this new number or new notation which is the infinity norm of F or the supremum norm of essential supremum norm of F. We are going to discuss now properties of this L infinity space that we have just introduced together with the norm function that we are bringing in. So, the first observation that we make is that the mod F function, F is a real valued measurable function. So, therefore, modulus of F is a non-negative measurable function. This is true pointwise. So, therefore, you have this general inequality. Therefore, as a consequence of that, if you follow the definition of essential supremum, you will have immediately that essential supremum of mod of F, which is the infinity norm of F, must be non-negative. This is just by construction. Consequently, what you are having is that this mapping that we have defined earlier from the L infinity space, for each function it associates this number, but this number now is a non-negative real number. So, that is by construction, and this number is taking values possibly including 0 up to infinity, infinity excluded. So, therefore, that is the structure of this infinity norm map. But let us look at these further properties in the light of our earlier discussion. So, the first thing that we will do is that we will look at the almost everywhere equivalence again. If it so happens that the L infinity norm of this function F is 0, then immediately if you follow the steps that we have been discussing so far, then you will immediately get that the function F must be 0 almost everywhere. This follows, as I said, follows by the similar arguments that we did for the usual LP spaces, and therefore, as a consequence of that, we will again be able to talk about the equivalence relation on this collection of functions, and therefore, this will give you a collection of equivalence classes up to this almost everywhere equalities. But then again, to reduce the notational difficulty, as we have done before for the usual LP spaces, we will follow the similar notational terminology that we work with these equivalence classes only, but do not stress on the distinguishing an equivalence class and a representative function from that class. So, essentially we will think of these equivalence classes as functions inside this L infinity space only. So, this will reduce our notational difficulties, but let us move on and we will see that this again gives us similar properties that we have seen for the usual LP spaces. So, start with L infinity function now. So, you are assuming that essential supremum of modulus of F should be finite, and also choose a real number alpha. This will act as a scalar. So, we are now asking for the scalar multiplication property. Then for any non-negative real number C, observe that modulus of F is less equals to C almost everywhere. This happens if and only if modulus of alpha F is less equals to mod alpha times C almost everywhere. This follows by standard verification, and therefore, as soon as the L infinity norm of F is finite, therefore, you will have the essential supremum of mod of F is finite. You can immediately show that the essential supremum of modulus of alpha F is also finite, and hence as a consequence of that, alpha times F, that is now a new real valued measurable function that satisfies the relevant properties, and it is now a element of that new L infinity space that we have introduced. And moreover, as a consequence of this equivalence that we have just proved, it immediately follows that the L infinity norm of alpha times F is equal to modulus of alpha times the L infinity norm of F. So, this is following our usual expectations, and therefore, we end up having the scalar multiplication property for the L infinity space. And more generally, if you follow similar arguments by similar straightforward arguments, you will end up having the additivity property that given two functions from the L infinity space, we can show that addition will give you again a real valued measurable function such that essential supremum of modulus of f plus g is finite, and therefore f plus g is a element of this L infinity space. Moreover, you can again verify that the L infinity norm of f plus g is less or equal to L infinity norm of f plus L infinity norm of g, and this actually gives you the triangle inequality for the L infinity norm, and therefore together with all these properties you will end up having the first, that L infinity space is a real vector space, and moreover this new function, the L infinity norm that we have been calling it, it is actually a norm on this space L infinity. That L infinity norm, first of all it identifies with 0 if and only if the function is 0 under the mu almost everywhere equivalence. Then there is this scalar multiplication property that we verified, and finally the triangle inequality holds for this norm function. So, we end up with the fact that L infinity space together with this L infinity norm that we have been discussing forms a norm linear space, and therefore you end up having again a metric topology, and you can ask for the similar properties about convergences of Cauchy sequences. And similar to the discussion that we performed for the usual LP spaces, we will look at Cauchy sequences, but now in this L infinity norm, and then once you have such a Cauchy sequences, you can justify this pointwise convergences and end up having a limit function which is again can be shown to belong to L infinity. So, therefore, you can establish the completeness of this L infinity space, and consequently you end up having that L infinity space together with this norm topology that we have, this metric topology coming from the norm, it forms a Banach space. So, that is a complete norm linear space. So, we have seen several related spaces related to the usual LP spaces that we have considered earlier, but now we are going to look at a relevant functional analytic property of these LP spaces which are called dual spaces. Dual spaces are collections of continuous linear functionals on the given space. Remember, as soon as you have this topology on these LP spaces, you can talk about linear functionals on top of it, and you can talk about whether these linear functionals are continuous or not. Now, if you have this collection of continuous linear functionals, by construction itself you can show that this forms again a nice Banach space. So, first you have to show it forms a vector space, then with the dual norm that we usually define from functional analysis, you end up having a complete norm linear space for the dual space structure. Therefore, these Banach spaces which are formed of these continuous linear functionals, they in some sense capture certain important properties of these usual LP spaces. Now, let us restrict our attention to P between 1 and infinity, 1 excluded, infinity also excluded. So, let us start with this situation. Then what can be shown by standard arguments, that the dual space of this LP actually is the LQ space, where Q comes from this relation, that whenever you choose P between 1 and infinity, strictly between 1 and infinity, then as soon as you choose the Q with this relation, so therefore for that Q, if you look at the LQ space, that can be identified as the dual of LP. So, this is a general nice structure that comes from the LP spaces. But now we can ask what happens to the excluded value of P. So far for LP spaces we have included 1, but in this specific discussion we have started by excluding the value 1. So, let us look at the L1 space and ask for the dual structure. Now, the dual space of L1 actually turns out to be identified with L infinity. So, this is also a nice property that L infinity can be identified with the dual of L1. Now, again you can ask that in this lecture we have also seen the P equal to infinity case which led us to this L infinity space. So, what is the dual of this L infinity? Now, as it happens that in general the dual of L infinity will contain L1 and typically be bigger than that, but the description of that in general is difficult because it will also depend on the structure of the underlying measure. So, to avoid the technicalities, in this course we are not going to discuss about the dual space of L infinity. So, in this lecture we have seen several related spaces to the usual LP spaces, and we ended up discussing this dual spaces of LP. So, we stop here, and in the next lecture we are going to see some problems based on the lectures or based on the material that we have covered in this week, and hopefully those problems will help you understand the material better. So, see you next time. Thank you.